This week's topic is interpreting geologic history through relative dating, which is to say we're going to learn how to read rocks. Learning your igneous, metamorphic, and sedimentary rocks is like learning your ABCs. Now it's time to learn how to read rocks, just like we're learning how to use your letters to spell words. So how do you read a rock? Well, here's a picture of a rock, and one of the things you'll notice is that the layers of the rock are going in different directions. There's different kinds of rock here, and hopefully by the end of this video you'll be able to look at a picture like this and it'll tell you a story about how it formed. This was all started by a guy named James Hutton. He's called the father of geology. His famous quote is that the present is the key to the past, which summarizes the principle of uniformitarianism, which we're going to learn about in a few slides. Like many of the scientists we've learned about so far, he was not taken seriously in his lifetime because his ideas were so big and replaced some very important wrong ideas. His most important student was a guy named Charles Lyell. He was better at explaining Hutton's ideas and so in a way that people could understand him, and so he actually became more famous than Hutton. He was also very influential to Charles Darwin. So here's the main idea that James Hutton came up with, and it's called the principle of uniformitarianism. And it basically states that the processes that shaped Earth are still happening today. Mountains are still being built and eroded in the same way and at the same pace that they were long, long ago. And this means that the Earth must be very old. You can see in this picture that we have some sand that seems to be breaking off these rocks above it, and that sand is turning into sandstone at the same rate that it always turned into sandstone. So that is where we get the idea that Earth must be very, very old. There's a couple other principles that you need to learn to be able to read rocks, and the first is the principle of original horizontality. It states that sedimentary rock layers are always originally laid down in horizontal flat layers. And the second is the principle of superposition. And basically it states when these horizontal rock layers are put down, the oldest ones are on the bottom and the younger ones are on the top. There's another concept, the idea of intrusions, and this states that when magma melts its way through layers of bedrock, it forms an igneous rock that is younger than the rock that it entered into. You can often see evidence of what's called folding, which is when you have sedimentary rock layers that are squeezed together to make these bent layers. And faulting is when that bending becomes so intense that it actually causes the rock to break along a surface called a fault. An unconformity is when a rock layer has been erased by erosion. So you can see here in the photograph we have these slanted rock layers that must have been tilted by folding or faulting, and then they don't continue. There was some sort of layer that was erased, and we know that because of the flat layer on the top, and that's an example of an unconformity. So when I look at a rock outcrop like this, I'm going to attempt to tell you how I would tell the story of this. And we know from the principle of original horizontality that water deposited the sediment and it formed horizontal layers of sedimentary rock that might have looked like this. And you can see the water on the top. Second, tectonic pressure caused the layers to fold, and additional pressure might have caused them to rip apart and fault. As this rock was exposed to weathering, it would have become flatter, so weathering and erosion levels the landscape. Water deposits the sediment on top, and it forms more horizontal layers of sedimentary rock. And then we see here that the magma from deeper inside the earth intrudes the rock, and we know this happened towards the end because it goes through all the layers. And the magma cools slowly, forming an intrusive igneous rock. So basically on the left we have a picture that I got off the internet, and on the right is my recreation of that picture step by step. In this video here we can see an example of another rock face, and we can see in three-dimensional modeling how this was determined, how this might have formed. So we see that layer A is the lowest rock in the column, and it's the only rock that is deformed. So by the principle of superposition, we know that in undisturbed sequence of strata, which is rock layers, the oldest bed lays at the bottom. By the principle of intrusion, we know that the layer B is younger than layer A because it penetrates layer A. So it's going right through layer A, cutting right through. Layer C is an erosion surface representing a time gap between the rock above and the rock below. So this is the unconformity. There is really no way to know if B or C is older, however. Layer D was deposited over unconformity C, and by the principle of superposition, we know that in undisturbed sequence of strata, the oldest bed lies at the bottom and successively higher beds are younger. Layer E is an erosion surface that formed when the lower layers of rocks tilted after deformation. This is called an angular unconformity. So here we see that all the layers are being tilted, and then it's being eroded and flattened off on the top. And then finally, that top layer, we see that more sedimentary rock layers were laid down on top. Here we see some sort of river that was depositing this sediment in layers on top of all the other layers. So you can try this for yourself in this diagram. We're going to be doing this in class, but if you have any questions, you can challenge yourself to try to identify putting this in sequence of oldest to newest. This diagram here is a cross-section of parts of New York State, and this is not far from where we live. It's a little bit further west, but you can see that if you were a person walking from left to right, the type of bedrock that you'd be walking over would change, and walking from left to right, you'd be walking from the older bedrock toward the newer bedrock, and you wouldn't see any kind of tilting, but you would be, if you look at this cross-section, you can see that all these layers started off horizontal and then were tilted upright. Here we have another map of New York State, and you can see that there are these layers of bedrock that go from east to west, and the reason that they change is because of the same thing we were just looking at. Different types of sediments and rock formations were laid down and eroded, and so the ages of these rocks changes as you go throughout the state. And here's how it looks in your reference table. Notice down here in the lower left, the type of symbol tells the age of the bedrock in each part of New York State. A fossil is the remains of a once living thing, such as a bone, shell, or imprint. Fossils only form in sedimentary rocks with a few exceptions, and the exceptions are pretty much volcanic ash. So how do fossils form? Well, first rock layers are deposited from the bottom up. We see here that we have a fish in the water. The fish dies and sediment is covered over it. The bones of that fish may be preserved in that sediment, either as an imprint or they're actually changing into rock. Then above that, maybe a dinosaur might have died and its bones are preserved. Above that, we have a primate. And then so a person looking for fossils would find that the deeper that they dig, the further back in time that they would see. Here we see another illustration of how you might be digging deeper into the earth to go deeper back in time. So the most important kind of fossil is called an index fossil, and if it meets two criteria, it is especially useful for relative dating, and it's known as an index fossil. And those criteria are: it has to be a species that's found over a wide region, which means that it's an animal or a plant that was everywhere. And second, it has to be a species that's only on Earth for a short period of time. So why are these useful? Well, let's pretend you're digging up a treasure chest. Let's say you open the treasure chest and you find some silly bands, a bunch of Michael Jackson CDs, and a basketball. So which object would be most useful in telling you how old the chest is? Well, the answer is the silly bands, because these are something that was only popular for a short time, whereas the Michael Jackson CDs or a basketball are timeless objects that people have had for many, many decades. Well, the index fossils are found on page 8 and 9 of your reference table, and you can see down here at the bottom there's all these lettered animals and plants and their fossils. And then if you look in this section here, it shows the time distribution of fossils, And so it would have a category of creatures, such as dinosaurs, and then it would have one type of dinosaur. So you'll see in the dinosaurs bar, it would have letter L, which is a Coelophysis, I think that's how you say it. And dinosaurs existed for that entire bar, but that one animal only existed for a short time. So if you find that one animal, that tells you that you're towards the late Triassic, and that helps you date other objects and animals and fossils that you find in that same layer of rock.